Hey everyone, I'm back. Sorry about the lack of videos lately. Everyone in our family took turns getting a really nasty stomach virus over the last week, so it's been a little rough in our house. So you may have already gotten through this assignment for the week, but I want to get a new video up for you all anyway, just in case. So today I'm going to do the video for Chapter 3, Landscapes Fashioned by Water, and either this evening or tomorrow I'll get Chapter 5 done for you. Find my mouse. So let's just go ahead and get started. I know you guys are pretty crunched for time with the accelerated semester. So we're really going to be focusing on a few questions in this chapter. So what are external processes and what role do they play in the rock cycle? How do these processes impact the landscape? So external processes include weathering, mass wasting, or erosion. And these are ones that are going to be primarily driven by water in this chapter. So when we talk about mass wasting, this is the downslope movement of rock and soil due to gravity. So there we go. A combination of physical and chemical weathering basically set the stage for mass wasting. So they don't cause the mass wasting event, but they are underlying factors. So what happens is you have some sort of weathering that occurs to create instability in the slope. And the slope is able to retain integrity until you get the introduction of either a lubricant or a vibration that interrupts the internal structure of a land slope. So for instance, a slump is usually due to the introduction of water, and that's where the slope basically drops down on itself, so you get this stair-step-in look. You have a debris slide, which is where the material just moves down slope in a really unconsolidated manner. A rock fall is primarily weathered rock, whereas debris slides or slumps are more of a soil and a rock blend. And then mud flows are where you essentially have liquefied soil that flows down slope in a manner very similar to water. So triggers of mass wasting, like I mentioned, water reduces the internal resistance or friction of the soil and rock components. In addition to that, it actually adds weight to slope. So if you have a slope made of soil and rock, that has a whole bunch of void, pore space in between the rock and the soil grains, and that pore space is filled with air. Well, when you introduce water, the water fills that pore space and has displaced all the air, and now that water is there and water has mass. So all of a sudden you've maintained the same volume but increased the mass, and this additional weight can really impact the stability and integrity. Oversteepening of slopes due to weathering or removal of vegetation. Roots keep soil in place. They hold the sediment there. They really, they're kind of like a glue that holds everything together. So when we cut down trees, try and reduce the vegetation down to just these nice manicured green areas, we're actually reducing the ability of a slope side to maintain its integrity and hold together. Additionally, earthquakes introduce vibrations that can dislodge rock and loose material. So like I said, we're going to focus on water specifically and how it has an impact. So the water cycle discusses how water moves between the ocean, the atmosphere, and land in the hydrologic cycle. So a process in the water cycle include precipitation, rainfall, snow, sleet, evaporation, filtration, the movement of the water through a soil or sediment ground system, runoff, surface water, and transpiration, or the uptake of water through plants and then basically exhaling the water molecules back into the atmosphere. So here's a really good image of it. We've got our precipitation, our surface runoff, our infiltration, our groundwater flow, the plant uptake, and the transpiration of that from the plants back into the air. This is a good image to learn, just a really basic example of the hydrologic cycle. So this cycle is powered by the sun. Water enters the atmosphere through evaporation. Evaporation is where you heat the water molecules until they transform to their gas phase and enter the atmosphere. Wind then transports it through the atmosphere, and then the precipitation either falls to the ocean or continents, If it falls to the ocean, it completes our hydrologic cycle, so it's a very short cycle. But if it precipitates to the continents, it has to go through a few more processes before it is reintroduced to the ocean. So some soaks into the ground, some flows over the surface. The water absorbed by plants and releases transpiration. And when we talk about evaporation and transpiration, we typically group it into a category called evapotranspiration, because it is extremely difficult to measure what uptake is due to evaporation and what uptake is due to transpiration. So we kind of cover it all under one umbrella and say that the movement of water from surface to atmosphere is done by these two processes combined. And precipitation in cold regions actually becomes part of glaciers, which are considered reservoirs. So it actually is removing water temporarily from the hydrologic cycle when they're trapped within a glacier system. So running water, or what we call surface runoff, is where after precipitation, the water, some water flows over the surface. The water then tends to become channelized into streams, and these streams start to intersect each other and become larger, where they eventually converge into a river system. So a land area that contributes water to a river is called a drainage basin, and these are separated by divides. So here we're just looking at some large-scale drainage basins. So this is an example of the Yellowstone River Drainage Basin, and it covers Yellowstone Lake, Billings, Montana, Miles City, and all the rivers that feed into Yellowstone River. Yellowstone River Drainage Basin is actually a sub-basin within the Missouri River Basin. And if you look, the Missouri River Basin is part of the larger Mississippi River Basin. So each drainage basin can be divided down into smaller and smaller drainage basin regions, depending on how narrow of an area you want to look at. So the Mississippi River Drainage Basin covers an extremely large area. But if we wanted to, we could look at the Ohio River Basin, which is a much smaller section of it, and we could determine just what feeds into the Ohio River. So do any of you know what watershed Jamestown is located in? I know a lot of you aren't actually in Jamestown, I think, so this might be a little harder for some of you to figure out. Now I'll get back to what drainage basin it's in a minute. So when I talk about drainage basins and divides, drainage basins are determined by what are called drainage divides. So drainage basins are typically made up of converging low points, and the divides are the high points surrounding it. So what happens is, if you have a ridge and you have a raindrop that falls right here, it can either go to the left or to the right. So if it goes to the left, it's in one drainage basin, but if it goes to the right, it's in another. Because if you look, a raindrop that falls here is always going to go down this way. It's not going to flow uphill and over, right? And a raindrop that falls here is always going to flow down, not up and over. So any water that is dumped out on either side of the ridge is always going to flow to the same direction. This is how we get what are called drainage basins, because water that falls, follow my cursor, water that falls here is always going to impact this side. It's never going to impact this other side here. So it just makes it easier when discussing contamination or rerouting streams, what kind of impact these would have, because it gives us a really defined study area. So Jamestown is actually in the Ohio River watershed. It just barely falls within it. And on a smaller scale, it's in the Chautauqua Lake watershed. But you can see we're really at the, part of the most northern section of the Ohio River watershed here. Now, I talk about drainage basins. They can fall in a number of distinct drainage patterns. So these are patterns of how the streams connect to each other. There are 4 common patterns. First is dendritic. It kind of looks like a tree. So if you look, you have all your primary streams feeding into larger ones before they all meet into one large trunk stream, giving you this really nice tree look. You can also get your radial. This is typical if you have a volcano. So if you are an isolated mountain, so you have a high point, so all water is flowing away from a single point, but into multiple directions. So each of these is a different drainage basin as it flows away from the volcano. Rectangular or trellis. So you get these really blocky joints. This is common on highly jointed bedrock, such as igneous materials. And then you can also get what's called a trellis. So you'll get these very defined primaries, see, with a bunch of little secondaries coming off of them. So what happens is you'll have secondaries coming down from these hills of resistant rock into these valleys of the less resistant. So you'll have water flowing parallel through these less resistant rock valleys, and we'll discuss more about these valleys in a bit. And you'll have your more resistant hill slopes with those secondaries coming down. So this is just showing the elevation of some land around the Jamestown area. So the higher the elevation, the more red, lower elevation is green. Oops. So what can you determine from our picture here? So if you look, we have our highest elevation regions here. So we have Lake Chautauqua, obviously, is a low area, so it's green. So we have what look like are probably some more drainage areas right here flowing through the Jamestown area. And then if you look, this is an overlaying of some of the streams. So here's what the streams are within the Jamestown drainage area. So if you look at that, Jamestown is what is considered a dendritic drainage basin. And if you look, dendritic is typically on uniform bedrock. Jamestown is primarily made of glacial till material. But glacial till is, the uniformly covering rock in the area. So it's all going to weather in a very similar way, giving you this dendritic drainage pattern. Now these drainage basins, so this is looking at an entire drainage basin. Drainage basins are also considered river systems, and this talks about the actual streams within it and the basin area. So when you talk about a river system, we've got our drainage basin, the whole area. That's just talking about the general, not geology, the general geography, basically, of it. But we also can break it, river system or a drainage basin down into 3 zones. You have your sediment production, or an area of erosion. This is where you have your very high steep slopes, where you're going to have a lot of weathering occur. Your sediment transport, which is where you're carrying all this material that's been weathered through the water, through your stream system, and then what's called your sediment deposition. Sediment deposition is usually where your river enters either a very large lake or the ocean. And as it's carrying that material, as it enters the ocean or the lake, the water slows down and it deposits all of that weathered material that it was carrying along with it. Now, water flows in 2 different ways. It can either be a laminar flow, which is where it flows in straight parallel lines, or turbulent, which is where it moves erratically in swirling motion. So turbulent is where you tend to see those, white caps or the white water in river systems. So here's an example of laminar flow versus turbulent flow. So the stream flow is important because this impacts its ability to erode and transport materials downstream. And the flows are also impacted by the velocity or speed of the water. So factors that determine the velocity are the gradient or slope. The higher the slope, the faster it's going to go down because that has more potential energy, right? So if you're up here, you have a ton of potential energy to move down slope. Whereas if you have something like this, you don't have a whole lot of potential energy. You're not going to move very far. Channel characteristics, the shape, size, or roughness. Larger size are going to give you more velocity. If you have higher roughness, that's more friction, so that's going to reduce your velocity. And discharge, the volume of water moving past a given point in a certain amount of time. Okay, the higher your discharge, the higher your velocity. So a longitudinal cross-section view of a stream, so if we're looking from the beginning of a stream to the end, it's called a profile. So we're looking at the head, the source, to the mouth, or the end of the stream. This cross-section looks at the entire stream and gives you a profile view, and this is typically a smooth curve, and it shows how your gradient and your velocity decrease downstream, because you have your higher gradient slope, so you're going to have your higher velocity at the very beginning, but by the time you reach the ocean, you guys have been to the beaches, I think, maybe. But if you have, you know it's a pretty low gradient, right? There's not a lot of hills, it's a pretty flat slope, so by the time it reaches the ocean, it doesn't have a high gradient, so it's going to have a much lower velocity. But as you move downstream, you're also going to increase in discharge and channel size because you're adding water from additional streams as you go. And sorry guys, I'm super thirsty today, so I'm going to be drinking while I record this video. So here's an example of a longitudinal profile of California's King River. So here we're looking at the head region. So this is just looking from one of the primary streams. You can see it's a very high slope gradient. And then as we move down out of the mountains, it starts to flatten out a bit. And then as we start to enter the beachy area near the ocean, you can see it's really starting to flatline. And then by the time it reaches the ocean, it is almost flat. There's almost no gradient change as it moves. Now the velocity is important because this helps us determine how a stream is going to erode or deposit. So streams erode by lifting loosely consolidated material. So loosely consolidated means they're kind of just sitting together, they're not cemented, they're not compacted. So it lifts them by abrasion or dissolution. And stronger currents lift particles more effectively. So here we've got the Holstrom curve, which looks at how streams erode and the velocities needed to erode certain grain sizes. So if you look here, at velocities of 20 centimeters per second and lower, you're not going to get any sort of erosion. You're actually going to get what's called deposition. See, the sedimentation of particles onto bed. So when you reach velocities this low, you're actually depositing material because you don't have enough energy to carry it with you. Once you hit about 20 centimeters per second, we enter what's called the transition zone. This is where we start to move into kind of scooting and picking up material. So here we start to pick up non-cohesive clay and silt. However, if you look, so the non-cohesive clay and silt aren't attracted very well. But if you get the cohesive, so the really packed clay and silt, you need to have velocities of almost 800 centimeters per second to start moving them before you would even reach active erosion. So active erosion of a clay or cohesive clay or silt doesn't happen until about 800 to 1,000 centimeters per second. So if you look at the sedimentation, it's pretty much the same up until fine sand. And then as the grain size gets bigger, you run into higher velocities of deposition. So once we're in like pebbles, we're looking at about 100 to 150 centimeters per second. We're still depositing. We're not actually eroding anything until we hit about 200 centimeters per second. So this shows that the easiest material for streams to erode is the fine to medium sand, because we can erode those right at about 50 centimeters per second speed in a very narrow transition zone. Everything else requires a significantly high amount of energy to erode it. So why would it take more energy to cause clay to erode than sand? Well, that's because clay is extremely fine-grained particles that attract together and cohese very, very easily. So they compact and stick together much easier, and it is extremely hard to break those bonds between the clay particles to begin eroding them. So once we start to actually transporting that material, it is what we call a stream load. Now, a stream load is broken down into different types. You can have your dissolved load. This is where the actual ions are dissolved into the water. Your suspended load, physical particles are carried within the water column. Or your bed load. This is where grains are moved, but they're just moved by scooting them across the base of the stream. They're not actually contained within the water column. So like I said, the dissolved load are ions from a chemical weathering and carried in solution. Suspended load are typically fine sand, silt, and clay that are transported without touching the bottom. They're held within the water column. And then the bed load is typically gravel and pebbles that are moved along the stream bottom by rolling, sliding, or what's called saltation. So they'll be temporarily picked up by the water and kind of hop along the base. Additionally, when we talk about this, we discuss the stream capacity, or the maximum load a stream can transport, and the competence, the maximum particle size a stream can transport. So the competence is determined by velocity. So if we had a velocity of 300 centimeters per second, then our stream competence could handle large size pebbles, but that's about it. It wouldn't be able to move into cobbles or boulders. If we had a stream velocity of 100 centimeters per second, the most it could do are granules or kind of gravel sized particles. The link to this has already been posted, so I'll let you watch that. But just let me know what happens to the boulders when the stream profile flattens out further downstream. I really want you to examine that and think about that question. Base level and stream erosion. So base level, when we talk about streams, is the lowest point to which a stream can erode. Now, there are only two types of base load. The ultimate, which is sea level. You can never erode below sea level. And then your local or temporary. These are typically impacted by natural events or man-made occurrences. And changing conditions can cause readjustment to your base level. So a rising base level means that you are undergoing deposition, and if you have a lowering base level, it means you're undergoing erosion. So rising base level means you're adding material, you're increasing elevation. And a lowering base level means you're removing material or causing erosion. So deposition of sediment is caused by a decrease in velocity. So like we said, the competence is reduced. So the decrease in velocity means your competence is reduced, so it can't carry grains as large anymore, so your sediment begins to drop out. Stream deposits are generally well sorted and called alluvium. Well sorted means that stream deposits tend to do what's called a fining upward gradient. So you tend to have your largest grains at the bottom, because those are what fall out first as you slow down. And then as it continues to slow, it starts dropping smaller and smaller particles until the slowest flow is dropping the smallest particles. Okay, so as you decrease, so if you're slowing down, you're going to drop the heaviest stuff first, right? And then as you keep slowing and you can't keep up, you're going to drop the next heaviest stuff. So until you go to the smallest items. So this is looking at how a base level would adjust to changing conditions. So here we have just a typical stream profile here. And say we decided we needed to build a dam for some reason. So we built a dam and a reservoir. So we had a base level of, 100 meters in elevation. Well, now we've built this dam, and our new base level has raised, 20 meters above our original elevation here. Our water is never going to go lower than this because of the way the dam is built and the deposition that is occurring because of the reservoir being placed here. This is all sediment that's been deposited because we've decreased the velocity and created this lake behind the wall. So lowering of a regional base level can be caused by uplift of the earth or a drop in sea level. And raising of the base level can be caused by a subsidence of earth or a rise in sea level. So if the sea level rises, then your base level of a regional section, not just a single stream, but a regional section would actually raise too, because it can't ever flow lower than where the ocean is, right? It's just going to flow straight into that ocean level. When we talk about streams, we also need to discuss channel types, because this can have an impact on how it shapes the landscape around us. So there are two main types of stream channels: a bedrock channel, which is where a stream is actively cutting into and eroding solid rock, and alluvial channels. These are composed of unconsolidated sediments, so broken up, already weathered rocks. And there are two common types of alluvial channels: meandering and braided. Meandering channels are like you see here, so it's a single channel that just kind of moves around in a lazy fashion, back and forth, all the way around. Most of the load in a meandering channel is in suspension. Okay, so some of it's dissolved, most of it is actual physical particles carried within the water column. It's not moving a whole bunch along the stream bed. It meanders, or it moves along in deep, smooth channels, and it mainly moves mud, so silt and clay particles. As the stream moves, it erodes on the outside of the meander, so right out here, or the cut bank, and it deposits on the inside, right in here, or the point bar. So this is a demonstration video. This is a good one to watch to kind of get an idea of how the meanders move. So meander channel, what happens is your normal stream in a straight section, maximum velocity is near the surface at the center of the stream. But as something displaces that stream due to uneven geology, the geometry of the stream isn't symmetrical, it starts to shift that maximum velocity to one side. As it does that, that higher velocity is going to start removing more material, right? Because the higher velocity, the more stuff it can carry and load. And it starts to remove that. But then you've got this much slower velocity on the other side. So it's so much slower, it's going to start depositing material because it doesn't have as much energy to carry it within the stream column. So you've got high energy eroding here, low energy depositing in here. And then as you move, you've got your straight stream profile, but then that high energy moves to the outside again and erodes here, and the low energy is depositing here. And as streams move, they start eroding further and further out until they start to get a very, basically a very narrow curve where it starts to almost look like it's pinching itself closed. So these stream channels can then shape their own valleys. So a stream valley is the channel and surrounding terrain that contributes. The valleys are shaped by weathering, overland flow, and mass wasting. And there are two general types, narrow and wide. Narrow valleys are V-shaped, so the very abrupt shaped valleys. They're typically headwaters, so they're typically where a drainage basin or a stream system starts. These are actively downcutting to achieve their base level, so probably sea level. And the features often include rapids or waterfalls because it's a very high energy, high velocity region, a lot of erosion going on, a lot of potential energy at this point. Wide valleys are typically already at or near their base level, so they don't have as much potential energy. And the downward erosion is less dominant because of this. So it's probably still transporting material, but it's not actively removing material now. And here the stream energy is directed from side to side in meander pattern. So what happens is most stream valleys start as these narrow V-shaped valleys with a lot of energy, a lot of erosion going on. As they erode, they start to widen the valley system, and as the valley system widens, you start to get this loss of that potential energy. It's not as large of a gradient or slope now. And as it loses that potential energy, it starts to enter its meander phase. And as it meanders, it starts to widen its valley system. Until after a period of time, you have a very well-established river that has developed a very wide, very large floodplain region from its constant meandering and moving back and forth and erosion and deposition patterns. And finally, we need to talk about deltas, the depositions of these stream systems. So deltas are where sediment from a stream enters the lake or ocean, like I mentioned back in the very beginning. This is from a sudden decrease in velocity. So what happens is your stream has a certain amount of energy as it's moving down. And even though it loses energy as it reaches the mouth or the end of the river system, it still has, a certain amount of speed, a certain amount of flow. And that speed relative to the velocity in a lake or an ocean is significantly higher. So even if it's moving only at 10 centimeters a second, your lake doesn't have a velocity at all, really. It might have an outflow somewhere, but it's not on a scale of centimeters per second or meters per second. We're talking millimeters a minute kind of deal. So you have this huge change in velocity. So all of a sudden you went from being able to carry this material and load to you have no energy anymore. So if you're moving along, and all of a sudden you basically hit a wall and you can't move anymore, and all that stuff's going to drop straight out. And that's where we get deltas. It is basically the instantaneous deposition of all that suspended load. New Orleans in Louisiana is actually built on an abandoned delta of the Mississippi River. So all that was sediment that had been carried down the river and deposited in a single point at some distant history. Oops, there we go. An additional depositional landform that most people don't think of are called levees. So these are natural levees that form parallel to the stream. So there are definitely man-made ones where we kind of build up walls around rivers to keep them from flooding a region. Natural levees happen when a stream or river system floods, and as it floods and overruns its bank, it deposits some of that material, because as it overruns, all of a sudden it's encountering friction here, so it starts to slow down as it overflows the bank. Then it deposits its coarsest grained sediment. So it builds up this little natural levee as it recedes back to its normal elevation. And then another flood event will come. It'll take more energy to get up and over that old levee, so it's going to deposit its coarse material again. And so it starts to build up this natural levee after numerous floods. And after each flood event, it's going to take higher and higher event floods for it to break over its natural levees. So floodplains, like we mentioned back a few slides. So these are flat, low-lying regions of a stream valley. So what happens as the stream meanders back and forth, occasionally as it floods, it will, overrun its banks, deposit coarse material by the stream, but then it deposits a whole bunch of the finer material out and around it, like you see down here. And so this is a huge depositional area where it's starting to deposit that sediment during flood events, building this very uniform, very flat landscape around your stream. A lot of people use regions like this for farming because these sediments and these flood events tend to be very high in nutrition. However, building houses near a stream or a river in a floodplain region like this is usually not recommended because the occurrence of your house getting flooded is significantly higher than anywhere else. And then here we've got what are called valley walls. So this is the furthest extent that this stream has ever moved laterally during its development. And it kind of bounds in your floodplain region. Additionally, a cutoff. So we talked about the meanders getting this really narrow point. So a cutoff is when the meander slows due to a resistant material, and the upstream meander catches off and erodes the narrow neck between the two. So, okay, let's break that down. So you've got a stream coming down, and it goes around this curve and up and around and back over. But after a while, it takes a lot of energy to get around and back to where you were. And then either through a flood event or a high energy event, basically the stream hits a point where it takes less energy to run over the overland straight into where it is again than to go around these curves. So it basically breaks over a natural levee and meets up with the other end of itself here, you can see right here, continuing on the stream rather than going around these huge curves. And this abandoned section then is what's called an oxbow lake, because it looks like the hooks that they would put over oxen to pull carts. And these are abandoned meanders of a river system. You can actually see them all around the Mississippi River drainage basin. So your stream basically gets to the point where there's less energy required to jump a levee and meet up with itself downstream than to make it all the way through this large meander curve. Another feature are called back swamps. So these are areas of floodplain where the fine sediments settle after a flood. So really it's just the section right behind the natural levee. All the fine sediment tends to accumulate here, and it tends to stay a little watery because that water then gets trapped in that region behind the levee. It doesn't recede back into the stream or river system as the flood moves out and recedes. Floods are probably the most common and destructive geologic hazard that exists that we know of right now. Floods can be both natural and human-induced. Heavy rains, rapid snows are naturally caused but can be exacerbated by human activity. Dam failure, topography, and surface conditions are typically human-made. Engineering issues causing a dam failure, topography if humans change the landscape, change the elevations, pave over floodplains, surface conditions if we make previously permeable surfaces such as fields and forests into asphalt blacktops where you don't have any way to get rid of the water as it's coming down. These are going to be a few videos of some significant flood events. Some of them are from New York, some of them are from China, just showing the massive amount of power and energy and destruction that these flood events can have to really change the landscape, both natural and man-made. This one's a really astonishing video when you watch the floodwaters moving through here and taking down entire skyscrapers. Now, we've talked about surface water and how it changed the landscape, but we can't forget about groundwater. So I'm going to take another drink. So groundwater is the largest freshwater reservoir that we have for consumption. And it has a variety of geologic roles. It's an erosional agent. It dissolves bedrock material that moves through, creating sinkholes and caverns. And it also equalizes stream flow, and we'll discuss that in a few minutes. So this is just showing the distribution of fresh water. So 85% of it is trapped within glaciers. Groundwater is 15% of all fresh water on Earth, and then the remaining, like 0.9%, not even 0.8%, is contained within lakes and reservoirs, moisture within the soil, water vapor in the atmosphere, and river water. So just a small amount is actually surface water that we have available for consumption. So, how does groundwater exist within the system? So we break it down into a few regions. We have our region of soil moisture, our zone of aeration, which is called the unsaturated zone. This is the pore space that is filled mainly with air. So we have soil moisture that's contained within the soil, but it's primarily unsaturated. It's mostly air particles. Then we enter our zone of saturation. This is where the pore spaces are filled with groundwater. Now, when we talk about the water table, what we're saying that is the water table is the upper limit of the zone of saturation. And if you go deep enough in the Jamestown area, typically more than 500 feet, the groundwater can be salty, and sometimes saltier than seawater because it is dissolving so many ions from the bedrock that it's moving through that it's actually dissolving, sodium, chloride, potassium, all the different salts, and giving it that very salty feature. So this is just showing the subsurface when we talk about groundwater. So we've got our unsaturated zone, or our zone of aeration, and then we've got our zone of saturation. So right here, this boundary right here, that's our water table. And your water table typically intersects the surface at a stream. So stream areas are usually where your groundwater elevation is equal to your surface water elevation. Now, sometimes you can get what are called perched water tables. This is where you get a layer, either a rock or really tightly packed clay, that keeps the water from entering all the way to the water table. It just kind of sits on top of this. And this can actually cause springs to come out from the side of like a hillside area, because this water is still got a lot of potential energy. It still wants to reach that water table elevation. So if it can't get through this aquitard, this limiting layer, it's going to push through the soil at some point where it meets the air surface and then flow as surface runoff into a stream. When we discuss groundwater movement, we talk about how it moves through the pores in the soil or the bedrock. So porosity is a term hydrogeologists use. This is the volume of pore space in a soil or rock, and it is expressed as a percentage of the total rock or soil volume. So sand has a porosity of about 30%. And this determines how much groundwater can be stored. Permeability is the term we use to discuss the ability to transmit water through connected pores. Okay, so this is how easily water can move from one pore space to another. So an aquitard is an impermeable layer that doesn't move water through it easily. And an aquifer is a highly permeable layer of material that allows water to move through it easily. So clay has a porosity of greater than 50%. However, all that pore space in clay are extremely disconnected. So because of that, clay has a permeability of almost 0%. So you can have a high porosity and extremely low permeability, whereas sand has a porosity of 30%, but a very high permeability because that 30% is very well interconnected, making it extremely easy for water to flow through. Additionally, we have some subsurface features that can be seen at the surface. For instance, hot springs. This is where water is warmer than the local air, typically heated by the cooling of igneous rocks. So this is water that's actually heated from below the surface. And then geysers are hot springs below the surface that intermittently reach the surface. This is where the water turns to steam, so it's heated to steam within the subsurface and then wants to reach the atmosphere, now that it's in a gas form, and essentially erupts. Old Faithful, obviously, is a really good example of this. Artesian wells are wells where the water rises higher than the groundwater level. This usually happens if you have like a curved bedrock region like this. So what happens is you have the water entering this curved area between two impermeable layers. So it's trapped right within this layer. So it tends to fill it up to an equal elevation on both sides. Now if we put a well in, just sticking up right here, if we poke it down into this first one, it's not gonna be artesian, it's just gonna rise to its normal level. But because we've got these impermeable layers here, it's trapping that water, it has nowhere else to go. So if we put a well in here, if we only have the top of the well right above the land surface, we're gonna have water shooting up until it reaches the same elevation as the saturation level. Whereas if we installed the well but the top of the well was up here, the water wouldn't come out of it. I'm not going to test you on the artesian wells because honestly this is a concept that is much better dealt with in greater detail in a hydrogeology class. But if you want to examine this image more, so we get a recharge and it's moving through a permeable layer that is bound by two impermeables. And so it doesn't have anywhere to go, so it's trapped within here, so the water basically keeps backing up through our permeable layer to a higher elevation. So if you punch a hole in it at the lower elevation, that water is going to want to equilibrialize. I don't think that's a word. It's going to want to equilibrate. So it's going to want to go to the same elevation as, the water drops here want to be at the same elevation as the water drops here. So it's going to shoot up vertically to try and equilibrate itself, giving you those artesian wells. And then most houses in my area, I'm in a very rural area, use wells instead of municipal water. So wells are a primary water source for a lot of us. These are pumping groundwater for consumption. The pumping can cause a drawdown, or what's called a cone of depression in the water table. So as we pump, it's just temporarily lowering the water table because we're pulling the water out at a rate higher than it's coming in. So if you pump a well too hard, you can actually pump it dry because you pumped all the water out faster than the water can move into it. Now the importance of this is because if we have a homeowner and they've got a well down into the water table for their consumption, and so here they've got a well down into the water table to use to irrigate their field, and then this guy says, you know what, this well over here is not doing a good enough job. I want a new high capacity well. It's going to go a lot deeper, it's going to pump a lot faster and a lot harder. So you put that new one in, all of a sudden it's got a cone of depression down throughout the well system, and it's pulled the water table lower than the home well and the other field well. So now this homeowner well is basically a dry well because this high capacity irrigation one is pumping the water so fast it has significantly dropped the elevation of the water table. And groundwater is a non-renewable resource. It renews, but it renews extremely slowly. We're talking it could take 100 years to recharge a groundwater system. So an increased withdrawal and a drought can equal a long-term drought that can take decades to recover from. Or an increased demand could actually cause a widespread groundwater depletion because you're now pulling water from all around the groundwater system and it's not able to recharge at all from any region around it. Additionally, groundwater withdrawal can cause what's called land subsidence. This is where the water is pumped out faster than it's replenished. And as the water is removed, now all of a sudden you've got that empty void space, right? It's air again. But the weight of the overburden, the weight of the soil above it, is now too much for that subsurface to hold, and it actually compacts and collapses because that water was actually supporting some of the weight. So this photo here shows how groundwater depletion has affected California's Central Valley. So over a period of about 50 years, the groundwater actually, the ground surface actually subsided about 9 meters. Okay, so the ground used to be at an elevation about here 50 or so years ago, and it has just been slowly compacting and subsiding ever since. Additionally, groundwater contamination can be an issue, especially in areas where the aquifer is a significant part of the local water supply. And groundwater pollution can be from farming industries. Farmers just dump their waste on an area that happens to be very permeable against the groundwater system. Industry dumping sewage, sewer systems, old sand pits that have been abandoned are sometimes areas for likely contamination because if they're not correctly closed down. Some old landfills have been put on top of these sand pits, and all that contamination from the landfill actually seeps down into the groundwater system. Groundwater is typically mildly acidic, and it actually contains a weak carbonic acid, so it's slightly acidic, which means it's able to easily dissolve calcite, right? Because our hydrochloric acid, when we tested our calcite on our mineral samples, or you saw the pictures of that. So the hydrochloric acid actually causes it to effervesce, or it fizzes, so it's basically causing it to dissolve. So if you have a mildly acidic water flowing through a limestone, which is made of calcite, it starts to dissolve the calcite in that limestone. And as it does that, it starts to create pockets of eroded areas. And as this happens, it creates what's called a karst topography. So this is where you dissolve limestone near the Earth's surface. This is an area that typically lacks good surface drainage. So it all enters into that limestone bedrock system, causing sinkholes. These are surface depressions where the acidic groundwater dissolves the bedrock until the subsurface actually collapses very quickly underneath the overburden, opening up the sinkholes. Those have been in the news a lot with a lot of rain happening out west. That's common where the groundwater or the moving water very quickly removes a bunch of material, causing a sinkhole. And caves and caverns are actually caused by karst topography and the dissolution of limestone. The cave system, I don't know if any of you know Penn's Cave in Pennsylvania. It's a very large cave system you actually raft through. The water moving through that, basically an underground river, has dissolved enough of the limestone that it creates these massive cave systems that you can go into. So this just shows the karst topography. You've got your stream moving through with a very high water table. You got a couple sinkholes opening up where the water table has caused the instability of the overburden. As your stream starts to cut down, your water table elevation starts to drop. And as it drops, now you've got these open caverns that have lost their water support, and so they start to collapse in on themselves, causing sinkholes. And as these sinkholes collapse, and over time, so the water starts to erode these openings and widening these openings out, but then as the stream drops the water table level again, your water starts to preferentially flow through these collapsed sinkholes and these openings within the limestone to get to the water table, and further erodes these until you get these open caverns or caves. So here's a picture of an extremely large sinkhole. I'm not actually sure where that region is, but it's an extremely old sinkhole too, but it shows you how the subsurface had eroded the material down here until it couldn't support any of this overburden anymore, and that collapsed into it. And now it's just this large open hole to what used to be a groundwater system. This is someone who tried to build a house in a highly karstic region, and their house was basically swallowed by a sinkhole. The caves and caverns, like we said, are formed by dissolving rock below the surface. And common features of a cave are stalactites. Those are, those rocks hanging from the ceiling, and stalagmites that grow from the floor. There we go. So stalactites hold tight to the cave roofs, and stalagmites might grow to touch the stalactites. Well, what these are, the way these are created is as the water enters these systems, the water kind of moves along the surface area, and as it drips down, it precipitates out some of those ions that dissolve. So the water becomes oversaturated with these ions, and it has to release them somewhere. So as it moves along the roof, it actually precipitates that calcite back out. And as it drips, it starts to build and accumulate. So let's find a stalactite. I can't even find a good one. Here. So as the water is kind of condensing on basically the roof of this cavern, it's oversaturated, so it needs to get rid of some of those ions. So as the water drips down, it leaves behind those calcite ions, and then they start to accumulate into larger and larger formations until you get the stalactites. And then the stalagmites, as the water drops down into stalagmites, and as it sits there, it precipitates out even more of that calcite. And so the precipitation of that starts to build on itself and cause these stalagmites to grow vertically. So that is your chapter 3. Again, sorry the video is super late. I'll get the other one up tomorrow. If you have any questions about that, like I said, please do not hesitate to let me know.